Welcome back to Chemistry Corner. I'm your host, Mr. Sellers. So a little bit of an update on the spread of COVID-19. We've moved up, the CDC has ramped up their recommendations, and they're now saying that groups of 10 or more is like too large of a gathering, and we should try to keep it 9 or less to try to prevent the spread. That is just a guideline though, so it's still okay to go to the grocery store and get what you need. We also, unfortunately, had our first death in Indiana. It was an older woman over 60, and she did have pre-existing conditions, but it just shows that this is a very serious thing. You know, just a few days ago we didn't even have any cases in the state, and now unfortunately we have our first death due to the coronavirus. Anyways, our video for today, I thought that we would talk about oxidation states. Today is going to be the due date for that ionic compounds megaset, and the last thing that you should have to fill out is the column that has the oxidation states in it. So we're going to go over a few examples for this, we're going to go over definitions, and then at the very end we're going to start to take a look at polyatomic ions and how we can find the oxidation state of those. Alright, let's get it going. Alright, so I thought I'd take it outside today. I want to talk about oxidation states. This is something that we've covered in class, and we have done a few examples of. We learned that railroad method, and then we had a whole practice day right before we had the shutdown. So this should be familiar to most of us, but I know that our attendance has been a little bit spotty. Some of us might have missed this. I want to go over it again. So when we think about oxidation states, the oxidation state, or sometimes we say the oxidation number, it is the number of electrons gained or lost by an element in a compound. So if we think about that, what all these words mean. A compound is a molecule that has 2 or more elements. An element is a type of atom. So if we're thinking about the oxidation states, it's if we think about one atom, did that atom gain electrons to form this compound, or did it give up electrons in order to form this compound? We've learned that with ionic bonding, there's always this transfer of electrons in order to make the compounds. So all I'm pretty much looking to find out is, did this element gain electrons or did it lose electrons when it was making this compound? When we think about writing out the oxidation state, it'll usually be in the top right corner here. So there's lots of things that we can draw with our element symbol here. Typically, looking at your periodic table, you'll see the atomic number on top and the average atomic mass on the bottom. Sometimes it'll be flipped, but you can always tell because the atomic mass will be larger than the atomic number. And then it'll also usually include decimal points if it's an average. And then the oxidation number, what we're talking about today, will be in the top right corner. Same place as the charge. That's because the charge and the oxidation number are very related. A lot of the times they're even the same number. We will see a few times where we can't really call it a charge, where it's more appropriate to call it an oxidation state. So let's work on solving a few of these. As always, we'll start with some easier examples, build our way up. So let's start with the easiest ones. The easiest things to tell our oxidation states for are going to be the elemental forms and the monatomic ions. Let's start by talking about the elemental forms. The elemental form of an element is the state that it's naturally found in. So if we think about metals, it'll look like it has no charge to it, like iron or copper or gold. But not everything is found, as a monatomic element. Some of them are diatomic, like some gases here, like hydrogen gas or nitrogen gas or oxygen gas. These things will be diatomic. We'll see them move around in groups of 2. But when it's in the elemental form, it hasn't formed any bonds yet, aside from the diatomics, but it hasn't formed any bonds, meaning it hasn't lost any electrons, and it hasn't gained any electrons either. In the case of the diatomic elements, they're exactly equal in their electronegativity. So it's not like one of them can steal the electrons completely from the other one. They've got this perfect interchange of electrons where one of them is sharing its halfway and the other one is sharing its electron halfway as well. So they each end up with sort of like half of both electrons, which is kind of the same charge-wise as having one electron. Anyways, the oxidation number works out to 0 for the elemental form. Now, if we think about making these elements into ions, that's when we're going to see the charge come in. The monatomic ions are going to have some charge to them. The nice thing about that charge is that it'll match the oxidation state. So that's why we took the time to write the common oxidation states for a lot of these elements onto our periodic table. It won't work every time. For example, all of these on the top row here are transition metals and they have variable oxidation states. I gave these ones specific oxidation states, but they could change. So, for example, this is iron 3 right now, but we've seen in lab and we've seen in other places that it could also be iron 2. So that's just kind of an off thing. The transition metals and then also tin and lead will have variable oxidation states. They can change the number of electrons that they give or take. Looking at our diatomic elements as examples over here, when they become ions, they're going to break their diatomic bonds. They're going to break apart from each other and bond with something else. So hydrogen, nitrogen, and oxygen, they've all got their common oxidation states. When they're not bonding with themselves, some of them tend to become a little bit more greedy, more electronegative, like oxygen and nitrogen are gaining more electrons. And then some of them, like hydrogen, will actually choose to gain more electrons, or I'm sorry, to give up their electrons, forming a positive charge. So for the elemental form, 0 every time. For monatomic ions, the charge is going to be the same as the oxidation state, or we can say that it'll be the common oxidation state for that element. And then the variable charges have variable oxidation states. Now let's see what this looks like in an actual compound. When we take these ions and actually bond them together, how does that change the oxidation states? Or does it change the oxidation states? Let's find out. You ready for this, Lua? Can you give me a high five? High five? Yeah, thank you, Lua. Alright, so how do we actually solve these oxidation states? If it's not in its elemental form, and it's not a monatomic ion by itself, then how can I determine what the oxidation number is? We actually have a set of rules that'll go through this. I'm not going to repeat all of them again here. You might hear me say them. But if you want that complete list, you should check the PowerPoint slides, or a quick Google search will also turn up the oxidation state rules. But I'm going to go through these 3 examples here. And remember, these are all ionic compounds. These first 3 days we were working on all ionic compounds. Starting with this one over here, magnesium chloride. So looking at this compound, I want to use the railroad method to determine the oxidation states of both, of magnesium and chlorine. Remember that to do this, we're going to draw 2 parallel lines going underneath, and then we're going to draw a perpendicular line that intersects those parallel lines, sort of like a railroad track. It'll end up looking something like this. Oh goodness. I wouldn't want to drive on those railroad tracks. Anyways, now I need to go and try to determine the oxidation states for both of these elements. I've got magnesium and I've got chlorine. There's no rule about chlorine, so I'm going to skip that for now. Looking at magnesium though, there is actually a rule about magnesium. It says that all of the alkaline earth metals of which magnesium is one, those are all going to have an oxidation state of +2. The reasoning there is that these are very electropositive elements, meaning that they would actually prefer to give up their electrons in order to get to a lower energy octet. If they give away their 2 valence electrons, they can get to a stable octet at the energy level down, the next lowest energy level. So for magnesium, I'm going to put an oxidation state of +2. For chlorine, I don't have a rule. I'm going to make it a variable. At this point, I need to multiply down by my subscripts. So I've got 1 magnesium. 1 times 2 is just 2. Beautiful. And then for chlorine, I've got 2 of them. So instead of just saying X, I'm going to say plus 2X, since I've got 2. And then you see that I set it equal to 0. Remember, that's because this is a neutral compound. Both of these oxidation numbers need to cancel out to get to that neutral charge of 0. Doing some quick algebra here. 2 plus 2x equals 0. My x here is going to be a -1. And that works out. -1 is the common oxidation state for chlorine. It gets both of them their octet. So my answer's here. For magnesium, it's +2. For chlorine, it's -1. Moving into the middle example here. This is iron 3 oxide. Iron 3 oxide. Using the railroad method to determine these oxidation states, I'll get it set up first. Much better. I'm still trying to get to 0. This is still a neutral compound. I'm going to start with oxygen. I do have a rule for oxygen. It says that oxygen is always going to be -2. I know that oxygen will always be -2 because it's extremely electronegative. Oxygen wants to gain 2 electrons in order to fill its octet. And it's got the strength to do that. Its nucleus is very positive, with not much electron shielding. That lets it pull in these other electrons much closer and attract them to give it an oxidation state that's negative. Iron's going to be my variable this time. Iron has a variable charge, a variable oxidation state. So this is a pretty common type of problem we're going to run into. I'll multiply down by the subscripts. 2 times x, that's 2x. 3 times -2, that's -6. And then I'm going to set that equal to 0. Now I've got another algebra problem that I'll need to work out here. 2x minus 6 equals 0. That's going to tell me that x equals +3. And that makes sense. Earlier I said that this was iron 3 oxide. That means that the oxidation state of the iron is going to be iron 3. Iron with a +3 charge, iron 3. Moving into my last example here, this is calcium carbonate. It actually has a common name too. It's called calcite. This is found in limestone a lot. We've got a whole bunch of this here in Indiana. Solving the oxidation states for calcite, for calcium carbonate. I'm going to have 3 answers this time. 1 for calcium, 1 for carbon, and 1 for oxygen. I'll set it up the same way. Get my railroad tracks going. This is a neutral compound. I'm trying to get to 0. Oxygen will be my first go. And oxygen will always have an oxidation state of -2. That's because it's so electronegative. Calcium. Calcium's an alkaline earth metal. It'll always have an oxidation state of +2. That's because it's so electropositive. Carbon this time. Carbon is my one that's going to be a variable. Carbon's a really interesting element for a lot of reasons, but one of those reasons is because it has 4 valence electrons. That's kind of right in the middle of an octet, which means that it could give up its electrons, it could gain more electrons. There are lots of ways to stabilize carbon, which lets it bond in really interesting ways. Multiplying by my subscripts, that's my next step. 1 times positive 2, that's positive 2. 1 times x, that's another x. And 3 times negative 2, that's a negative 6. All of that is set equal to 0. So 2x plus x, positive 2 plus x minus 6 equals 0. So doing some quick algebra here. If I combine these terms, that's a negative 4. X minus 4 is 0. X equals positive 4. And then this all adds up. So my carbon this time is going to give up 4 electrons. It'll lose these 4 electrons. That'll still give it a stable electron configuration. It'll actually be a duet then. But that is still stable. So all of these elements are now happy. In class, we did a lot of this practice with the railroad method. This is something that I'm going to be testing you on when we get back, or we may end up having to do it on an online test. Regardless, though, this is something that will show up on the final. The last little bit that I want to do today, I want to try some of these with just looking at the polyatomic ions. It's going to be pretty much the same. I'll go through 3 examples. I might pick up the pace a little bit since I've already covered the basics. Let's do it. Alright, home stretch here. Thank you again for making it this far in the video. The last thing that I'd like to do is talk a little bit about the polyatomic ions and how we can solve the oxidation state for a larger ion when it's not a neutral compound, when the charge doesn't cancel out. So I've got 3 examples here. Let's start with the ammonium ion over here. I'm still going to use the railroad method. I'm still going to set this up just like I did in the last little segment. Let's see if I can do better this time, though. Okay, that's not bad. I'm happy with that. Yeah, I'm cool with that. So, I set it up slightly different. I still have my railroads in place. But instead of having a 0 in this position, I put a positive 1. That's because the charge for an ammonium ion is positive 1. Overall, this ion has given up an electron to some other particle, and that gives it this positive charge. So when I do all my oxidation states this time, it's not going to get to 0. I'm trying to get to positive 1. I'm going to start with nitrogen. I'm going to start with hydrogen because I do have a rule about hydrogen. When hydrogen bonds with non-metals, it'll be positive 1. When it bonds with metals, it'll be negative 1. You remember, hydrogen's a little bit flexible in that way. But the majority of the time when hydrogen is bonding with a non-metal, it'll be positive 1. So I can put that in. Plus 1. Nitrogen is my variable this time. I'll make it an X. I'm going to multiply by my subscripts, just like before. 1 times x, that's going to be x. 4 times positive 1, that's going to be positive 4. So beautiful. And then you can see I'm trying to get to, maybe you can't see, but this says x plus 4 equals positive 1. So x plus 4 equals positive 1. Doing some quick algebra there, I'm going to figure out that x is equal to negative 3. So it turns out that this time, nitrogen and hydrogen are going to have their common oxidation states. Nitrogen likes to gain 3 electrons. Hydrogen likes to give away an electron. So this one is pretty standard. They're both at their common oxidation states. That might not always be the case. Let's look at sulfate. I can reach this one better. So sulfate is going to have a charge of -2. So I put -2 in this space that I'm trying to solve for. I'm going to start with oxygen. Oxygen's very electronegative. It wants to gain 2 electrons. I'm going to give it those electrons. -2. Sulfur is what I'm trying to solve. I'll multiply by my subscripts. X times 1 is x. -2 times 4 is -8. And that's all equal to -2. So I've got a little algebra problem set up here. Doing my work, I'm going to find that x is equal to a positive 6. This is where I start to see students making mistakes. When the oxidation state doesn't match the common oxidation state. So, drawing a quick example here. Normally, sulfur would like to gain 2 electrons. That'll give it the octet at the higher energy level, and it'll be very stable that way. And gaining 2 electrons, that's a much smaller transfer than giving away 6 electrons. But in this case, when sulfur bonds with oxygen to make a sulfate ion, that sulfur is actually going to end up giving away electrons instead of gaining electrons. So it'll give away 6 electrons. It still ends up at an octet, it's just the octet at an energy level lower. So why does it give away electrons instead of gaining electrons? It's because of its partner. It's because of who it's bonding with. Oxygen, I've said it a lot, it's so electronegative. It's going to steal those electrons away from sulfur, even though sulfur would like to gain its own electrons. Sulfur is not strong enough to fight oxygen. Oxygen will be the one to gain those electrons, or gain the majority of the control over those electrons. Let's try one more example. A nitrate ion. Setting up my railroads. I'm going to set it equal to -1 this time. That's because nitrate has a charge of -1. Oxygen's always -2. That's a good place to start. Nitrogen's my variable. Multiplying by the subscripts. X minus 6 is equal to -1. So this time, x is equal to 5. A positive 5, I should say. This isn't the common oxidation state. Commonly, nitrogen is found at -3. But now I'm telling you that this nitrogen is at a positive 5. It's because it's bonding with oxygen. When nitrogen bonded with hydrogen, nitrogen was more electronegative. That means that nitrogen had the power to steal those electrons. It was the stronger one. That's why it gained 3 electrons. But over here, it's like nitrogen made it to the big leagues. Now it's fighting oxygen. Oxygen's stronger. It's not a pushover like hydrogen is. Nitrogen will try to steal those electrons. It will try to get into an oxidation state of -3, but it's going to fail. Oxygen's more electronegative. Oxygen's going to be the one that's stealing those electrons. 2 from each oxygen, or 2 for each oxygen, I should say. So nitrogen is the one that has to give away 5 electrons. You might see a little bit of discrepancy there. 3 times -2, that's -6. Oxygen needs 6 electrons for each oxygen. But nitrogen's only giving up 5 electrons. That means that the nitrate ion as a whole, this whole polyatomic ion, is going to steal 1 electron from some other particle. Maybe it's sodium nitrate or potassium nitrate, lithium nitrate. But this nitrate ion will get this extra electron from some other particle that's not on the board here. Or maybe it was actually ammonium nitrate. Maybe this nitrate steals an electron from ammonium, and then they end up at these charges. What I'm saying is that this charge, this electron, comes from an outside source. And that electron is going to an outside source. So we've gone over oxidation states. We did it for elemental forms, for monatomic ions, for neutral compounds, and for polyatomic ions. You should be set to finish that ionic compound set, get all 3 columns done for all 20 chemicals. That is due at the end of the day today. I set the due date for, I set the deadline for midnight to give you a little bit more time. I don't know at what times in the day you'll have access to the internet, especially if some of you might have parents working remotely from home right now. Tomorrow, we will start talking more about covalent compounds and the nomenclature for those covalent compounds. It should be another short video lecture. And then next week, remember that we're on spring break. I won't be sending out any more video lectures. I might post something, but it won't be an assignment. It'll just be more of a greetings or an update maybe. But it won't be anything that's due. When we come back from spring break, if we're still on this e-learning, my lectures might end up getting a little bit longer because I'm going to need to start teaching new material. And it'll probably take me a little bit more time to come up with a video that can convey that material in a way I feel like you can learn it. I'll probably also have some assignments from the textbook if we're not back in person. Honestly, I'll have assignments from the textbook even if we are back in person, so you can be expecting that after break. Alright. I hope that you are staying safe. I hope that you're following the guidelines from the CDC and from the World Health Organization. Wash your hands, follow the news, and stay calm. Calm is contagious. Have a good one. I'll see you again tomorrow for Chemistry Corner. Lua, come here, Lua. You want to make an entrance? Can you get up here? Yeah. Good girl. Bye.